Hi everyone, I am Yuan Xiao from the Ohio State University. The topic of my presentation today is one-bit flops, one-cloud flops, cross-VM Rowhammer attacks, and privilege escalation. The paper is the joint work of Xiaokuan Zhang, Professor Yinqian Zhang, Professor Radu Teodorescu, and me. What we did has something in common with the previous talk. We both exploited Rowhammer in cross-VM settings. However, we do not need any presumption of the settings of the hypervisor, and we'll see how it goes. Let's start with some news from the internet. The first one is in 2014, by when the DRAM disturbance error was first reported in academic papers. Rowhammer attack is based on such error. In March 2015, the Google Zero project presented the first kernel-level exploitation with Rowhammer. And not long after that, some researchers showed that Rowhammer could be triggered with JavaScript. In other words, even a website page on your browser is able to do the attack. And recently, DDR4 DRAMs were also proven vulnerable, although they were once designed and thought to be immune. Different from previous work, our research focused on strengthening it by enabling double-sided Rowhammer, and we exploited its power to break software isolation on the memory in cross-VM settings. Before we move into the attack, I would like to provide some basic ideas of the DRAM organization and architecture. The memory system in your computer is organized on a hierarchical basis. The DRAM modules are first divided into one or multiple channels, each consisting of one or multiple DRAM modules. Each module is actually called a DIMM, dual inline memory module. Each side with chips is called a rank, and each black chip includes multiple banks. A common number of banks is 8. The banks consist of a number of memory blocks. A memory block is recognized as bytes. They are organized in a two-dimensional way, indexed by their row number and column number. While the chips have their own buses and are standalone from each other, when referring to a certain bank index, the banks with that index in all the chips will be loaded simultaneously and be combined into a 64-bit word. Now let's see how to access a memory block in a bank. Every square in the figure is a memory block, and they all have their unique physical addresses. First of all, the DRAM will charge the row where the block locates. We call the charging here a row activation. Now the row is loaded into a structure called row buffer. Each bank has its own row buffer. And then the block is chosen by using its column number from it. If the next block to access is still in the same row, there will be no activation of the row. The block can directly be accessed from the row buffer. Now we can move on to the Rowhammer vulnerability. Before we do anything, the DRAM is normally maintaining the values. The figure here shows a single bank with a buffer. Notice that each square here stands for bits rather than a bytes for convenience. Now we wish to access the block in the row between the two gray rows. We charge it before we access it from the row buffer. After that, we access a block in a different row but still in the same bank. Now the row buffer contains the second row, and we access the first row again. Since we have to load it into the row buffer, we have to charge and activate it again. By accessing the two rows in turn, they are charged and activated in all the accesses. The rapid row activation will lead to some electromagnetic influence on these neighboring rows, and finally it will cause some bits in neighboring rows to charge or discharge and be changed into a different value. The value change is called a bit flip. It may be 1 to 0 or 0 to 1. And the flipped bit is called a disturbance error. And the attack to trigger bit flips by intentional rapid row activation is the so-called Rowhammer attack. Now imagine the two rows we use in the Rowhammer are so close that there is only one row between them. Naturally, the middle row will be influenced by both rows, causing the chance of bit flips to be much higher than the upper and lower rows. So a stronger type of Rowhammer attack is called double-sided Rowhammer, while the previous one is called single-sided Rowhammer. Although the concept of double-sided Rowhammer was suggested long ago, none of the previous work correctly conducted in modern processors. These projects are quite interesting and helpful, like Seaborn from Google presented kernel privilege escalation and sandbox escape. However, no exploitation was ever done in the cross-VM settings. Here comes some questions leading to our research. How to conduct double-sided Rowhammer attacks, and how to exploit rockhammer vulnerabilities in cross-VM settings. Our work on rockhammer attacks falls into 3 parts. In the first section, I'm going to introduce a novel method to reverse engineer the physical address mapping of DRAMs. Thus, we have enough knowledge to bring forward the accurate and efficient double-sided rockhammer attacks. The second part is about how we exploit arbitrary memory access by rockhammer attacks in the cross-VM settings. Rockhammer serves as an excellent tool to break the isolation of virtual machines. In the end, I will talk about a sophisticated attack against OpenSSH server based on the previous 2 sections. Now, let me introduce to you the first section, the reverse engineering of DRAM mapping. Remember our first question, we need a way to find 2 rows in the same bank, and there is only 1 other row in between. However, Intel keeps how physical addresses are mapped to the hardware a secret, and different CPUs, different DRAM types and sizes all lead to different mapping rows. So given 2 physical addresses, how do we know which bank and which row are they mapped to? Or more specifically, are they in the same bank or neighboring rows? We make use of the timing channel to analyze the memory block with the physical addresses x1 and x2. Suppose x1 and x2 are mapped to 2 different banks, b1 and b2. We want to first read x1. We activate the row here. Activation takes the activate time, and we load it into the row buffer. Then we read it from the row buffer, and reading takes the read time. Then we want to read x2. We do exactly the same bit as before. Activate row, loading to the row buffer, and read. After the first run, we read x1 again. Now, since the row buffer still contains the row x1 is in, we directly read it without activating it again. And the same happens to reading x2. After reading x1 and x2 in turn for n times, the total time will be 2 times t activate plus 2 times n times t read. Now let's consider the situation where x1 and x2 are mapped to different rows in the same bank. First, we read x1, activate, loading to the buffer, and read. Same steps for x2. Here comes something different. Since the buffer now contains the row of x2, we have to activate the x1 row and load it into the row buffer again before we read x1. And the following reading of x2 also requires activating and loading before reading. As a result, there are more operations in each following round of reading x1 and x2, and the time consumption grows to 2 times n times t activate plus 2 times n times t read, and obviously t2 is greater than t1. To conclude, if we witness a high latency when accessing 2 physical addresses in turn repeatedly, they are definitely in the same bank but different rows. This is the basis of our method. So what can we infer when the 2 addresses are different only in specific bit positions? We can use the timing primitive to determine the physical address mapping, but we have to do it bit by bit. For example, we want to know what bit 20 is in charge of. We choose 2 physical addresses only different in bit 20, while the other bits are exactly the same. We read x1 and x2 in turn for a number of times. In practice, 1,000 times of accesses already makes the result clear. And we measure the time we use to do all the readings. If we witness a high latency in the timing, we know that x1 and x2 are mapped to the same bank but different rows. Then we can conclude that bit 20 decides the row, but it does not decide the bank. After doing the first test on all bit positions, we find the bits that only control the row index, and we call them the row bits. We pick one of the row bits and an unknown bit to do the next test. Again, we choose 2 addresses that differ only in the chosen 2 bits. In this case, bit 20 and bit 4. Then we read them in turn for a number of times. If we witness a high latency in timing, then the 2 addresses y1 and y2 are also in the same bank but different rows. In previous tests, we know that bit 20 is a row bit and has nothing to do with the bank. And since changing bit 4 also does not change the bank, bit 4 does not decide the bank either. Given bit 4 is not a row bit, it can only be a column bit which only decides the column index. We do the second test on all the unknown bits. Some of them will be recognized as column bits. Thus, we already identifies the row bits as in blue and the column bits in yellow. However, we still have no idea what the white bits are. They show low latency in both previous tests. Are they all bank bits which decide the bank index by themselves? The answer is no. In practice, by simply counting the real bank number, can we infer that the actual bank number of bank bits is smaller than the number of white bits here? The truth is that in the physical address mappings, there exists such a relationship. While bit 18 decides the row, the result of bit 18 XOR bit 16 decides the bank. We call such a scheme XOR scheme. So how do we determine such an XOR scheme? Similar to before, we first pick two addresses, only different in bits 18 and bit 16. Bit 18 and bit 16 are both the white bits whose job we do not know from the previous two tests. We read them in turn and take the timing of accessing them as before. If a high latency is witnessed, they are again in the same bank but different rows. In other words, either bit 18 or bit 16 decides the row. However, row bits tend to be higher bits for efficiency issues. Putting row bits on higher positions help reduce the bank duration. Bank duration means frequently changing a bank's currently activated row. So in this case, we take bit 18 to be a row bit. However, bit 18 has more jobs than simply designing the row index. That's why we didn't recognize it in the previous row bit detection tests. Let's take a comprehensive look at the truths we already know. Test 1 is the result of the previous row bit detection tests, and bit 18 is the only different bit in the two tested addresses Y1 and Y2, while bit 16 remains constant. However, X1 and X2 cannot be in the same bank and the same row because bit 18 decides so. So they can only be in different rows, also in different banks. Test 2 and test 3 are the current tests we are taking. We change both bit 18 and bit 16 in the two tested addresses. We know that Z1 and Z2 are in the same bank but different rows. Now let's calculate the value of bit 18 XOR bit 16, and let's focus on the XOR column and the bank column. With this simple table, it is clear that the result of bit 18 XOR bit 16 decides the bank index. Thus, such a setting of XOR scheme is corresponding to our test results. However, this is just the most basic version of the XOR scheme. There exist such complicated mapping schemes involving multiple XORs. In these cases, our graph-based bit detection algorithm is required to decode them. On the right are the schemes, and on the left are the corresponding graphs. However, there's not enough time to cover them all, so please refer to our paper for more details. After we have the knowledge of how a physical address is mapped to the DRAM, we are able to do accurate and powerful double-sided Rohammer attacks. And our next step is to make as much use as it possible to do the hacking in the cross-VM settings. Cross-VM Rohammer exploitation catches our eyes because virtualization is the core of cloud computing. Let's take the Xen-based cloud services as an example. A physical machine provides services with virtual machines to the users, and all the virtual machines on a single physical machine is managed by the hypervisor. Our attack technique is proven effective under Xen Para-Virtualized settings. And Xen PV is widely in use by multiple cloud service providers, including Amazon EC2 and Rackspace. In the Xen guest VM, the physical addresses used by the kernel are no longer the real physical addresses of the hardware. We call them pseudo-physical addresses, while the real physical addresses are called machine pages. If not in non-virtualized settings, a virtual address can be converted into a physical address by looking at the page tables. Luckily, in Xen PV, we are also able to do so to get the machine addresses. There is only one layer of the page tables in Xen PV, and this is the basis of our double-sided Rohammer. What's more, all the entries in these page tables point to machine page addresses. And another important point is that all these page tables are directly maintained in the guest memory space. Now let's go a little deeper into the page tables. A virtual address is divided into several segments. Each segment is an offset to a certain level of page table or to a normal machine page. When looking at the machine addresses, the kernel first gets the address of PGD from the register. Then it uses the PGD offset segment to find the PGD entry containing the address of PUD. The lookup continues in similar ways until it finally gets the machine address. Although all page tables are directly maintained in the guest memory space, they are read-only to the guest kernel. All the changes to the page table need to be checked by the hypervisor. When a guest wishes to modify its page tables, it needs to make a hypercall to the hypervisor, and the hypervisor will check whether all pages pointed to by the page tables, no matter a lower level page table or a normal machine page, are in control of the requesting guests. If the check passes, the changes are permitted and the controls are given back to the guests. If not, it is not allowed and there will be a fault. Knowing how Xen PV manages the memory, we can now talk about how we exploit arbitrary memory access regardless of VM isolation by using Rookhammer. The attacker is a normal guest VM, and the goal is to be able to visit any memory page on that machine. Before we do the attack, we can visit a legal machine page controlled by the attacker by its virtual address. Everything inside the dashed boundary here belongs to the attacker VM. The first step is to forge a last level page table where the entry is pointing to arbitrary page regardless of whether it is controlled by the attacker. The most important trick here is that the forged PT has the same machine address as the original PT except one single bit in a specified position. For example, on the screen, the address of PT and forged PT only differing bit 18. The reason to choose bit 18 will be soon explained. Let's go back here and move on to the next step. The second step is to copy the PMD, the second level page table, into the vulnerable machine page containing a flippable bit. The flippable bit should lie in the entry pointing to PT, and the position of the flippable bit in the PMD entry should be the same as the different bit in the addresses of PT and forged PT. In fact, we need to find the flippable bit before we do the attack, and we decide the bit index based on the position of these flippable bits. From now on, we call the vulnerable page a shadow PMD. Since the shadow PMD is exactly the same as the original PMD, we can safely replace the original one with the shadow PMD via hypercall. The hypervisor won't notice anything wrong. Now let's pay attention to the red arrow and the flippable bit in the PMD entry now. Here comes our hammer. By hammering the entry of the shadow PMD, page 18 is flipped. Since the new page it corresponds now as the forged PT, we successfully bypass the surveillance of the hypervisor and put the forged PT into use instead of the original PT. And any access to the original virtual address will finally touch an arbitrary page. What's more, we still have write access to the forged PT since the kernel and the hypervisor both still regard it as a normal page. It means that we literally can access any page we want to visit. After having access to arbitrary pages, we are now able to conduct numerous interesting attacks. There are two such examples in our paper, but I can only present you with one of them since the time is limited. If you are interested, please refer to our paper for more content. Coincidentally and interestingly, the OpenSSH is the target again, but in a much different way. Our sample attack is to bypass the authentication when logging onto an OpenSSH server. The prerequisite is that the attacker VM shares the same physical machine with the OpenSSH server VM. Our primary goal is to log onto the OpenSSH server without legal credentials by modifying some of the code of the server process. Shown in the figure is a snippet of the code in assembly. Notice that the second line in the graph is a judgment of whether the authentication result stored in register EAX is 0. If not, the authentication fails. So our target is to change the code so that every time the authentication is requested, EAX always contains 0 as a result. Originally, the first line of the code calls the function PAM-authenticate to allow password authentication, and it stores the authentication results in EAX. We change it into directly writing 0 to the register. The machine code of both instructions are 5 bytes long, so it is a perfect replacement. Now let's see in detail how the attack is brought out. Our attack applies to the daemon SSHD process so that all the connections afterwards will bypass authentication. First of all, the attacker VM conducts a page table replacement attack described in section 2 and tries to gain access to the memory space of the server VM. Then it searches for the 5-byte machine code of core PAM authenticates. Although the 5-byte pattern seems to be too short, we found that it was unique on our experiment machine in our tests. Once the pattern is found, we change the code into move 0 to EAX by directly writing to the memory. By then, we finish our attack. The time consumption of our attack depends on how many pages we need to search. If the code is the first page we search, the complete attack takes only about 0.3 seconds, and to search one extra 4 KB page will take about 58 microseconds. Now let's see a demo of our attack. Before we do the attack, we open the terminal of a VM on the test machine and try logging onto the server VM, also on the same machine. However, we cannot log in because we do not have the password. It will try different authentication methods, but anyway, we cannot be in. And at this moment, we do the attack from another VM on the same machine. We first conduct the page table replacement attack. We need to map a memory buffer to find the pages that meet our requirements. After the preparation is done, we do the rollhammer. Thus, we have arbitrary access and start searching for the 5-byte pattern. Once it's found, we change it into move 0 to EAX, as showed. Now we can try logging in again. We are directly in the server without inputting anything. There are a number of existing countermeasures against rollhammer attacks. ECC is a common solution and enables the memory to do single error correction or double error detection. DDR4 was once thought to be immune, but it was also proven vulnerable recently since TRR is removed from the DDR4 standard. Using hardware-assisted virtualization adds an extra layer of page tables and hides the real machine address from the guest kernel. But it's replacing Xen PV is rather slow for efficiency or other issues. To conclude, we use timing channel to reverse engineer the physical address mapping to the DRAM, and double-sided rollhammer is possible only on this basis. And we successfully break the Xen PV memory isolation by rollhammer. Further attacks are also proven viable. That's so much of today. Thank you all for coming and listening to my presentation.
This was great. So again, we have time for some questions. So I guess I can start also. So what would it take to fix these DRAMs so these rollhammer attacks are not possible?
You mean the countermeasures?
Well, these are countermeasures that would be implemented in the memory controller, but would you do these in DRAM, or why aren't they implemented today?
Actually, can you repeat your question once?
Well, why aren't these countermeasures already in place today so that the attack would not be possible?
All right, because actually our attack is still about rollhammer, and it's just a more powerful type by the double-sided rollhammer. And the existing countermeasures makes the rollhammer attacks much harder, but still they cannot be fully exterminated. And if we apply these countermeasures correctly, then of course our attack may also lose effects. However, like I said, like the HVM is a perfect protection against our attack. However, for HVM is slightly slower than PV, and also some cloud providers hesitate to switch to HVM for other issues like the cost issues, money issues. So it's actually the protection against the rollhammer are rather slow. Well, of course, I think most of the cloud providers are now using ECC DRAMs in their servers. But we still suggest that all the cloud providers can switch to HVM for the security rather than just sticking to the PV to save money.
Yeah, makes sense. Makes sense.
Thank
Thanks
you.
a lot. Any other questions? Okay, in that case, let's thank the speaker again. Thank you.
Thank you.